When you're training neural networks on flat images, standard architectures work fine. But the moment you step into 3 dimensions, everything breaks. A molecule's energy, a material's conductivity, a protein's folding pathway, they're all governed by geometric symmetries. Rotate the system, translate it, reflect it, and the underlying physics shouldn't change. Yet most traditional networks treat spatial coordinates as just another input channel, completely ignoring these invariances. That's why equivariant graph neural networks exist. They're built to respect the mathematical structure of 3-dimensional space, organizing features into irreducible representations, so that rotations and translations are applied through proper group theoretic operations. The model doesn't just guess. It enforces transformation rules that guarantee outputs change predictably when the input geometry moves. But here's the catch. Despite their mathematical elegance, these models are notoriously rigid. Most equivariant architectures are handcrafted for a single task. You build one to predict molecular energies, and suddenly you need it to reconstruct atomic structures from coarse-grained models, predict local magnetic properties, or generate new 3D geometries. You're usually rewriting the data pipeline, the message-passing layers, and the loss functions from scratch. The architecture, dataset semantics, and training objectives are tightly coupled, making reproducibility and cross-task transfer incredibly painful. That's where GEqTrain comes in. Instead of baking everything into the code, the researchers designed a configuration-driven framework that treats data semantics, model composition, and training objectives as fully decoupled, interchangeable modules. You define your input geometry, your equivariant layers, and your loss functions in structured configuration files. Change a few parameters, and the exact same underlying engine retargets to a completely different scientific problem. Let's see how this plays out under the hood. First, coarse-grained backmapping. In computational biology, you often downsample massive protein systems into low-resolution beads to cut simulation costs. But you lose atomic detail. GEqTrain takes those simplified coordinates, maps them back to full atomistic resolution, and does it by simply reconfiguring the input-output pairing and adjusting the reconstruction loss. No architecture changes. Next, they pivot to chemistry, predicting NMR chemical shifts in molecular crystals. NMR shifts are local scalar properties that reveal electron density and magnetic shielding around nuclei. The framework just points to a new dataset, declares the target as a local scalar, and lets the shared equivariant backbone handle the geometric feature extraction. Finally, generative modeling. They built GEqDiff, a diffusion-based extension. They tested it on a synthetic benchmark inspired by directional building blocks, where each unit carries a position, a shape descriptor, and a dipole vector. The model doesn't just predict positions, it jointly generates shape and orientation distributions. Because the geometry is configuration-driven, they can inject new geometric priors without touching the core message-passing logic. But flexibility only gets you so far. Even the most elegantly designed equivariant framework will hit a hard wall when you try to scale it to real-world systems. And that brings us to the second bottleneck, memory. Think about what happens when you feed a large molecular graph or a dense interaction network into a geometric neural network. You're not just storing node features. You're holding adjacency matrices, edge embeddings, activation states for every layer, and gradient buffers for backpropagation. In traditional full graph processing, memory scales linearly, then quadratically with system size. You hit VRAM limits, the runtime crashes, and the simulation dies. For materials discovery or protein folding, that's a hard stop. Researchers solved this by changing how the graph is processed. Instead of loading the entire structure into memory at once, they implemented chunked inference. You partition the graph into smaller subgraphs, process them sequentially, and handle the boundary conditions through careful message passing. Boundary nodes are duplicated or padded across chunk interfaces, so that local interactions are preserved without requiring the full adjacency matrix in RAM. It's the computational equivalent of reading a textbook chapter by chapter, instead of trying to hold the whole book in your working memory. The model extracts local features, aggregates cross-chunk messages, and moves to the next partition. The results are stark. On a nearly 30 million parameter equivariant model, the standard approach hit a hard VRAM ceiling at just over 11,000 data points. With chunking, the exact same architecture processed more than 28,000 points, without spiking beyond hardware limits. Yes, there's a compute trade-off. Sequential chunk evaluation adds overhead compared to fully parallelized full graph forward passes. But when the alternative is a CUDA out-of-memory error, that extra latency is a non-issue. You gain the ability to simulate larger systems, map denser interaction networks, and push geometric AI into regimes that were previously inaccessible. GEqTrain and chunked inference might look like separate optimizations, but they're solving the same underlying problem, making geometric AI actually usable at scale. One removes the friction of rewriting pipelines for every new scientific question. The other removes the friction of hardware limits when those questions get bigger. Together, they're shifting equivariant machine learning from a niche, research-only tool into a reproducible, scalable foundation for chemistry, physics, and materials science. Because the next breakthrough in drug discovery or battery design isn't just about better algorithms. It's about building systems that can actually handle the complexity of the real world. And that's where the real work begins.